Welcome to The Explainer. Today, we're diving into the literal fuel for modern agriculture, NPK fertilizers. You know, without these fascinating chemical mixtures, modern farming as we know it simply wouldn't exist. Honestly, our global food supply would just collapse.
Because to feed the world, we've got to solve a massive problem. You see, as plants grow, they literally strip the earth of vital elements. Over time, they completely deplete the soil of these essential nutrients. So the ultimate question for agricultural science is, how do we effectively put those elements back into the ground and do it on a global scale?
All right, here's our roadmap for this explainer. We're looking at 1. The magic of NPK, 2. Essential ions and compounds, 3. Sourcing the key elements, 4. Processing phosphate rock, and 5. Lab versus industrial production. Let's get right into it.
Section 1. The magic of NPK. Let's figure out exactly what we mean when we throw around the term NPK.
So the crucial point here is that NPK fertilizers are not just some random mix of dirt. They're incredibly carefully balanced formulations of different salts. And these salts contain exactly the required elements, in the precise percentages needed, designed specifically to help plants grow much larger and way more rapidly than they ever would naturally.
And what's really fascinating here is how each specific letter acts like a targeted multivitamin for a different part of the plant's anatomy. Nitrogen, the N, makes chlorophyll and protein, which gives you those rich, healthy green leaves. Then you've got phosphorus, the P, driving all its energy downwards to promote strong, healthy roots. And finally, potassium, the K. That promotes overall growth and the development of healthy fruit and beautiful flowers. It's basically a complete top-to-bottom care package for the plant.
Moving on to Section 2, Essential Ions and Compounds. Let's see how that biological plant recipe translates into hard chemistry.
Now, for plants to actually absorb these fantastic nutrients through their roots, the nutrients have to be in the form of specific water-soluble ions. Ammonium and nitrate ions, those act as our nitrogen delivery system. Phosphate ions provide our phosphorus, and potassium ions deliver the potassium. These ions are literally the raw building blocks for common fertilizer compounds, like ammonium nitrate, ammonium phosphate, and potassium sulfate.
And this brings us to a really crucial golden rule, especially if you happen to be facing down a chemistry exam. The absolute most effective fertilizers are the ones packed with the highest overall percentage of those three elements, N, P, and K. It is all about maximum nutrient density.
All right, Section 3. Sourcing the key elements. Now that we know the chemical recipe, where on earth do we actually find these ingredients?
Well, nitrogen is up first, and making its main compound, ammonium nitrate, requires this fascinating chemical relay race. First, we produce ammonia through the famous Haber process. And honestly, that breakthrough was so significant that without it, half the world's population simply wouldn't have enough food today. Just mind-blowing. Next, we convert some of that ammonia into nitric acid. Finally, we mix that newly made nitric acid with even more ammonia in a neutralization reaction to get our final product.
Now, compared to that complex manufacturing process for nitrogen compounds, potassium is remarkably simple. We can literally just mine salts like potassium chloride and potassium sulfate straight out of the ground. And because they're already in a form the plants can actually use, they can be added to our NPK fertilizers directly without any further chemical processing at all. Nature kind of did all the hard work for us there.
Section 4. Processing phosphate rock. This is where the chemistry gets quite a bit more intense.
So while we can mine phosphate rock from the ground, just like we do with potassium salts, there's a massive catch. Plants simply cannot use phosphate rock in its raw, natural form. It's totally insoluble. To unlock the phosphorus hidden inside, we actually have to treat the rock using several different concentrated acids. It's wonderfully ironic when you think about it, right? We have to blast rocks with highly corrosive acids just to grow a delicate little flower.
Here's how it works. If we treat the raw phosphate rock with nitric acid, we create a mixture of phosphoric acid and calcium nitrate. But the phosphoric acid, which holds that vital phosphorus we want, is still way too harsh for plants. So we have to neutralize it with ammonia, which finally yields usable ammonium phosphate.
But nitric acid isn't our only option to unlock the rock. We actually have two other pathways. Treating it with sulfuric acid yields a mixture of calcium phosphate and calcium sulfate, which the industry calls single superphosphate. Alternatively, treating the rock with phosphoric acid itself yields triple superphosphate. Both of these are incredibly effective, water-soluble sources ready for NPK blending.
And finally, Section 5. Lab versus industrial production. For our grand finale, let's compare how we make these life-saving compounds in a tiny school laboratory versus a massive industrial facility.
Focusing on ammonium nitrate, you'll see that safety and scale dictate completely different approaches. In a school lab, students use heavily diluted solutions, just to ensure safety. But out in the industrial world, time is money, and volume is absolutely everything. Factories rely on raw ammonia gas and highly concentrated nitric acid. It's vastly more dangerous, for sure, but entirely necessary for high-volume output.
Which leads us to a pretty mind-blowing feat of industrial engineering. While a student has to sit there heating their lab beaker with a Bunsen burner, industrial-scale reactions are highly exothermic, meaning they generate a massive amount of their own heat. So instead of wasting that dangerous heat, the factory captures it and uses it to power later stages of the operation. The process essentially powers itself.
Finally, let's talk about the sheer scale of production. The school lab uses what we call a batch process. You set up the equipment, make a tiny amount of fertilizer in one go, and then you stop. Industrial facilities, however, run a continuous process. The chemicals are constantly flowing, reacting, and churning out thousands upon thousands of kilograms of product without ever needing to hit the stop button. It's a true marvel of modern chemistry, totally designed to meet an insatiable global demand.
So as we wrap up this explainer, and you look back at how incredibly carefully we've engineered these vital chemical recipes, from raw-mined rocks and atmospheric gases, you kind of have to wonder, as our global population pushes toward 10 billion, how will we innovate these massive industrial processes next? What chemical breakthroughs are waiting just around the corner to ensure we can keep feeding the billions yet to come? Something to think about. Thanks for joining me on The Explainer, and keep questioning the world around you.